Okay, so at this point, you should be having finished the chapter on chapter 4, energy and matter, and completed that test your knowledge or the chapter quiz, whatever you want to call it. You should be working right now on finishing chapter 5, which is gases. And so you should look into Blackboard. There should be a discussion question, and then that you will respond by posting a response to that discussion question. And then there should be a test your knowledge test that you'll take. The test, they vary from 25 questions to 50 questions. You can take the test as many times as you want. The system automatically is designed to take your highest grade. And of course, it's open book. So there's every reason why you should be able to really do well for the class. Each week, on Wednesday, I always tape the lecture. So the Wednesdays you're not here, you can see what the lecture was for that day. So the lecture today is chapter 6. We're going to talk about basic systems. So it's going to be a show and a tell of what I'm going to do. I'm going to go through on the whiteboard all the stuff that's included in chapter 6. And so we're going to begin. So the first point that the chapter makes is that it makes the point that this stuff, refrigerant in these containers right here, that they absorb heat. So if I take a refrigerant like this and I place it in this room and I don't move around the can, I don't do anything to the can but let it just sit here and stabilize, then the temperature of the refrigerant will be the same temperature of the air in this space, because it's going to absorb whatever the heat is. And so this can't be emphasized enough. In refrigeration, air conditioning, heat is energy. And so we don't make things cold. What we do is we remove heat from that. So the feeling of cold, that is the absence of heat. Heat's the energy that gets moved from the space where we don't want it to a place where it's okay to be. So the textbook uses this illustration that I actually think they stole from me, because I thought I was the one who started this. Refrigeration, the way it works is just as if you were in an old wooden rowboat upstate, and you row that boat out in the lake. All wooden boats always leak. Water would come up in it. So you'd have to bail the water out. Well, that's what refrigeration's like. It's like you're in that boat, there's that water that's bothering you at your feet, and you take a sponge and you put it down there, you soak up the water in the boat, and then you stick your hand over the sides and you squeeze the water out of that sponge back into the lake. So it takes that water from where you don't want it and put it where it doesn't matter. That's the same exact way that this works. But it's going to, the absorbing is going to take place in what we call the evaporator. The squeezing of the sponge is going to take place in the condenser. Because it's in the evaporator, we absorb that heat, and it's in the condenser we get rid of it. And so the condenser is on the outside of the house. We're going to move that heat to the outside, just like I squeeze that water out into the lake. I'm going to squeeze that heat out into the air outside. And so that is the analogy that's used, that water in the boat and the sponge. Refrigerants absorb heat. Refrigerant systems, mechanical compression, air conditioning, refrigeration systems, have two sides. It has a liquid side and it has a vapor side. It has a high side being pressure side, and it has a low side, pressure side. So when I say that refrigerant's in a liquid or a vapor, it recalls back when we did state of matter. The 3 states of matter says that things could either be a solid, a liquid, or a gas. In most times in what we do in refrigeration, we're working with 2 of those states, liquid or vapor. But there could be a time when we deal with a solid for refrigeration. That would be a special application, and the refrigerant that we generally use, it's dry ice. And they use that for transport of food and preservation of food. So you see that when transportation trucking industries may pack things in dry ice. So there is an application where we use a solid. Dry ice is interesting because it does not have a liquid state. It's one of the only thing I can think of in nature that you find that does not have the 3 states of matter. Solid, it goes to a solid, to a vapor, to a gas. So we have a high and a low side of the system. The heart of the refrigeration system, the heart of this system is the compressor. The compressor is what's going to move that refrigerant throughout the piping circuit, throughout that circuit that contains the 4 basic components: the compressor, the condenser, the metering device, and the evaporator. Those are the 4 points right there. The compressor moves that refrigerant. If it's using one of the old school residential split air conditioning systems like you have at your house, then it's going to move it at a constant flow rate. At a constant rate. And if it has a newer system, maybe a ductless system that you had that's installed in your house, then it's not going to be at a constant rate, it's going to be at a highly variable rate. But whether it's constant or variable, it's still what moves the refrigerant in that system. So a compressor can only handle refrigerant vapor. Or I could say gas in, gas out. If liquid refrigerant enters into the compressor cylinder, then it will cause that compressor to slug, meaning that the valve that is used as intake and discharge, very much now sounding like automotive. If any of you ever did anything with automotive on your own or perhaps in school, it's sounding a lot like that. Matter of fact, it looks exactly like that. You're going to see terms like top dead center, bottom dead center, that are definite references that you would have with pistons and things like that. So we have, instead of intake and discharge piston valves, we have reed valves. And they're flat pieces of metal. If any of you have a 2-stroke engine at home, maybe a dirt bike or something like that, that has the same exact valve. And so the liquid gets there, they're going to bend the valves. That's what's going to happen. That's called slugging. That ruins your compressor. Your compressor is the most expensive part of the 4 pieces of that system. Compressor is definitely the most expensive part. So it's the heart of that system. It takes low pressure gas and makes it into a high pressure gas. It takes low pressure, cool refrigerant vapor and make it into high pressure, hot refrigerant vapor. So here's where you get that change. Why do we even need to change? Why does there have to be 2 sides of the system? It has to do with the properties of whatever refrigerant we're going to use. Remember, it goes back to the very first statement. Refrigerants absorb heat. So if I have the temperature of this refrigerant, let's say this room right now is 70 degrees. If I want to absorb heat in this room, with the rule being hot goes to cold, what do you think? We're going to call on Anthony. What do I need to do to this refrigerant to make it absorb heat.
Like you're saying, just leave it here. You know, be by itself.
Right. So here's what Anthony's getting at. That if it's 70 degrees in this room, and we have the rule that hot goes to where it's colder, I need to lower the temperature of this refrigerant vapor to be less than 70 degrees. And the more I can lower this refrigerant vapor, the faster I can, absorb heat. So in my system, I need a way of lowering the temperature below 70, and then when the refrigerant flows to the outside, I need to use the same rule. Where it's hot, it goes to where it's cooler. So if it's 100 degrees outside, I need to raise the temperature of this refrigerant vapor to 130 degrees. Because 130 degrees is still a lot more heat than 100 degrees. So it's going to leave where it's 130 and go to where it's 100. So when I say things are warmer or cooler, those are relative terms to what the temperature is either in this space, which is the space, we would call this the space that we want to condition. That means to remove the heat from, or perhaps add heat to, depending on the season, right? Winter versus summer. Versus outside, which we call that ambient air temperature. So the compressor does that for us. The compressor raises that temperature so that we can take that refrigerant and we can move it to the outside. So I said that we use we're getting into, it's like shop class, right? Automotive class. This is a piston. This piston is used in a compressor. It's used in a compressor, we'll say, our compressors are sealed in these they're steel, carbon steel containment and containers, right? So they look like cylinders. But inside that cylinder is a piston that goes up and down. And so when this piston is at BDC, bottom dead center, if you look in your textbook, it gives you the volume of that space. So the volume of the space in the textbook example, when it is at bottom dead center, that means it's down as far into the cylinder that it can go. And you find that it is 8 inches, and with that superscripted 3, that means cube, because that's how we measure volume, is in cubic feet, cubic inches. Do we have any guys that are motorheads at all here? No? You? So, okay. So older cars, muscle cars, did they say, oh, that's a 4-point liter engine, or what did they use as a measurement? Cubic inches, absolutely, right? And do you know what that is a measurement of? It starts with a D. Displacement of, you're right, it's telling us it's the displacement of the cylinders, the size of the cylinder. So, like I said, very much like a refrigeration compressor, very much like an engine. So when they talk about displacement, how much power that engine has, they're talking about how much of this cylinder, how much of this gas can they get in there and then to compress it back up. So in this example of the textbook they gave us in chapter 6, when the piston travels up, it travels to a point where it can't go any further up, and that's called top dead center. And at top dead center, there's just a little bit of space left where we've highly compressed that refrigerant gas, raising the pressure, raising the temperature. And so in the example they gave, it went to a 1/2 inch cube of space. So it went from 8-inch cube to a 1/2 inch cube, and if you look at the ratio, that's 1/16 of the space that it had before. So when you really push in and compress that refrigerant, those atoms, the result is heat and much higher pressure. That's why there is a one-to-one relationship between pressure and temperature. And so the opposite happens when we reduce the pressure. When we reduce the pressure, that's what the job of the metering device is to do. Only job it has is reduce the pressure of that refrigerant gas. And it reduces it so that it reduces it if it's air conditioning. I'll tell you the number. Is exactly, they want to make that refrigerant gas vapor 40 degrees Fahrenheit. Want to be 40 degrees Fahrenheit so that air that's coming in a little bit above 75 degrees Fahrenheit will say, whoa, it's 76 degrees here. I'm going to jump inside of this refrigerant and I'm going to hitch a ride along with it because it's much cooler. And so you have a couple of processes that are going to go on for air conditioning. One is the heat is going to go into that refrigerant vapor. And the second is, if you ever seen a container, a steel container that holds water, and you see that it starts to sweat, that dehumidification goes on too. So every evaporator is a dehumidifier. But there's other things that are in basic systems as well. One is an oil separator. So what does that mean? Why do we need an oil separator? Well, here's the deal. At the bottom of what's called the sump, at the sump of our compressor is a pool of oil called refrigerant oil. This refrigerant oil can either be a man-made product or a product from nature, depending on the kind of refrigerant that it uses. So the oil mixes easily with the refrigerant vapor. Mixes easy with the refrigerant vapor. It travels throughout the system. So when you go out and you start doing HVAC work, the first thing you're going to do is you're going to buy 2 sets of gauges. You're going to buy one set of gauges that can be used with the synthetic oil, and then you want to have another gauge that's used with the natural oils. And it depends on the refrigerant. R22 would have been a natural oil. A 410A, which is what's in this container right here, this would have been a synthetic oil. You don't want to mix the oils because we cross-contaminate the systems. That's why the purpose of the 2 sets of gauges. So when you take your gauges on and off, what you're going to see is you're going to have a little bit of that refrigerant oil on your hands that you're going to have to wipe off. The oil travels throughout the system. And it's a good thing that it does, because there's certain things that we want it to lubricate. But we don't want too much oil in that system, because if there's more oil than what we want, what do we have less of? Refrigerant. And if we have less refrigerant, we have less refrigerant effect. So we don't want it to be so much oil that it acts as an insulator or that we can't absorb heat. So we put in a unit that's called an oil separator, and it collects the oil for us. And there's an illustration in the book that'll show you what it looks like. All oil separators generally work on a practice of gravity, because oil is going to be heavier than refrigerant vapor. What are the other pieces to the system that we're talking about? Well, condensers is one. The condenser, that's that one where I take the sponge and I squeeze it out. That's the one that says it may be 100 degrees outside, but that compressor raised the temperature of this refrigerant to 130 degrees. So that heat wants to leave that refrigerant and go to the outside air that we call the ambient air temperature. That's the job of the condenser. And to condense is to make a vapor go from being a vapor or gas into a liquid. So part of that, what happens when it starts to give off heat, there's going to be a change of its state of matter from a vapor, from a hot gas, to a superheated gas, into a subcooled liquid. And its next stop is going to be in the metering device. So that's the job of the condenser. The condenser is our sponge that we're holding over the side of the boat. So the condenser makes it into a liquid. Now some systems, residential split systems or commercial systems especially, have what's called a liquid receiver. I happen to have one. Here's a liquid receiver right here. There's a very complex piece of machinery here. All it is an empty can. It's strong can, but it's an empty can. And what does it do? It does what all cans do. It holds liquid. So this will just hold liquid refrigerant. It holds it until the system says, I need more refrigerant in the evaporator because I need to absorb more heat. So it's used in conjunction with a variable metering device, this liquid receiver. But that's all this thing is. It's an empty container that holds refrigerant. Liquid stuff. We also have, now everything that's on the liquid side is also on the high side of the system. Everything that's on the return from the evaporator to the intake of the compressor is considered the low side of the system. So liquid side, we have things called filter dryers and a sight glass. So filter dryers come in different sizes. This is a filter dryer right here. So a filter dryer does what its name implies. First, filter. What does it filter? It filters any kind of fragments that are floating in the refrigerant system. It captures those. Well, what could they be? Well, they could be a couple of sources. I think probably the one that you would see the most is that when they braze the copper lines, the line set, they did not use dry nitrogen to reduce the amount of interior oxidation on those lines. So some of that oxidized material are floating in the system. The filter dryer would capture that. So do filter dryers, like all filter dryers, occasionally need to be changed? The answer is yes, absolutely. That's a great point. The way that you tell a liquid line filter dryer needs to be changed, first off, filter dryers have arrows. So when you install this, do make sure you install it going in the right direction because it won't work out for you otherwise. But you can take, now there'll be copper lines on either side of this, right? You would shoot it on this side and on this side. And if you get more than a 3 degrees temperature difference, this is clogged. It would need to be changed. So now, filtering is half the job. What about drying? What the heck is it going to dry? Well, it's liquid refrigerant. Does it dry refrigerant? In a sense it does, but it dries any moisture that's gotten in there. The enemy of mechanical refrigeration systems is when we let air into the system. That's why we use a device called a vacuum pump to reduce the pressure in a system to a point that water boils even if it's 40 degrees, even if it's 30 degrees. We want to boil that water out of it, get that water vapor out, because that is an enemy of the mechanical compression system. So filter dryer, this has a desiccant quality that will allow it to absorb moisture that we maybe didn't get when it was vacuumed out. You always usually see this in conjunction with this. This is the sight glass. The sight glass, and it's in the liquid line, right? So the sight glass, you can actually see liquid refrigerant flow inside this. And the sight glass has this little color-coded button right here, and it tells you whether the refrigerant is in a dry state or a wet state. Does it have moisture from the air in it, or is it not? And so it'll tell you. When it's green, you're good to go. When it's yellow, caution. You're going to come to a stop because it means there's a lot of moisture. Now, what do? Well, you can recover the refrigerant using a recovery machine. When you're recovering the refrigerant, you can pass it through a filter dryer once, twice, several times. You try to get rid of that moisture that's embedded in that refrigerant, and you can re-vacuum your system to get it to dry out. So that was the liquid line filter dryer in the sight glass. Now that other device, remember we covered so far the heart of the system, the compressor, the condenser that we use to squeeze that heat out to the outside. The next one is the metering device. Now the metering device comes in in this case, for this lecture, we're going to say two varieties. A fixed metering device, like this, and a variable metering device, like this. So a fixed metering, now all metering devices do the same thing. Here's what they do. First off, not one BTU of heat is changed when a refrigerant passes through a metering device. It's not shed, it's not absorbed. What does change is this. We're going to change the pressure. Remember that liquid pressure was under high pressure? When it passes through the metering device, that pressure is going to drop. I'll give you an example. A residential air conditioning system using R22, most likely on an average summer day, the high side pressure will be 270 pounds per square inch gauge, and the low side pressure will be 69 pounds per square inch gauge. Now where do I get now I told you the typical day, I'm using typical summertime temperatures about 3 o'clock in the afternoon. So I know what the general ambient air temperature is going to be for Central Islip, New York, which is what we use at the airport. We use 85 degrees. That's the design outside temperature, we call it. The inside temperature is much more concrete because the inside temperature for air conditioning evaporator coils for residential systems is always 40 degrees Fahrenheit. And I can use my pressure temperature chart and see 40 degrees Fahrenheit, R22, what's that corresponding pressure? Always, whether it's using R22 or R410A as its refrigerant. It will always be 40 degrees. The pressures would be different, but it'll always be 40 degrees. Did I give you guys these yet? All right, so I'll give them to you today. The fixed metering device is set to drop it to a preset number of 40 degrees. It's based on the length of the tube. This is called a capillary, let me get this out of my hand. This is called a cap tube, capillary tube, and its diameter and its length will be what makes that determination to say, refrigerant, you now equal 40 degrees. It drops that pressure. The variable valve, the thermostatic expansion valve is variable. It also measures the temperature of the refrigerant at this sensing bulb here. And it's going to say, I need more refrigerant from this receiver right here in order to maintain that amount of temperature and how it absorbs. So it monitors the system and calls on reserve when it needs to. Or when it doesn't need to, it chokes back the refrigerant and it rests in this receiver tank. The discussion I had about intake reed valves. If they get any liquid refrigerant, it's going to break the reed valves, run the compressor. So what they have, and you can see a picture of it in your textbook, is an accumulator. The accumulator works with that sort of like gravity, and it uses the gas pressure that if there is any liquid refrigerant coming from the evaporator, it will fall into the accumulator and then turn it back into a gas, and then let it pass back to the evaporator, to the compressor, back to the compressor. So why would we design a system, an evaporator, that doesn't consume all the liquid and change it into a solid vapor? Here's the deal. When you're in the open lab and you're using the torch, hopefully they told you to get a bucket of water, kind of like the bucket over here. So water, if you have a hot piece of copper, it's much easier to cool it down, to remove that heat rapidly by dropping it into a bucket of water, of liquid water, as opposed to letting it dry out, cool down in the air. Now, will it cool down with the air? Yes. Will it take much longer? Yes. So there's also a rule with this. Liquids absorb heat much faster than gas. Liquids absorb heat much faster than gas. So the engineering thought of this is that when we design an evaporator, we want the evaporator to be liquid refrigerant as close to leaving that evaporator without it leaving the evaporator as a liquid. But they're walking that line. They want that liquid refrigerant in the evaporator because that's where the greatest absorption of heat is going to take place, with that liquid refrigerant. The very first refrigerators that were made, they were called low-side float systems. They would move liquid refrigerant into the freezer compartment, and then it would stop. The liquid refrigerant would stay in the evaporator in the freezer compartment, and the motor would stop turning, stop running. And they would just let that liquid refrigerant stay there next to the ice or the frozen product and just keep on absorbing heat, because that's what liquid refrigerants will do. They'll absorb all the heat that they can from that space until it finds equilibrium with that temperature. So accumulators is there, it's a protection device, it's there to make sure that we do not allow any liquid refrigerant to damage the compressor. Number 11, suction line. Here we're going to get into one of those things that are relative. I said warm and cool are relative to one another. 130 degrees or 100 degrees. If it's 100 degrees outside, that's friggin' hot, right? And if it's 130, that's even hotter. So they're relative to what each other are. Suction line, liquid line. This is going to be really complex. We're going to really get into big science. Big suction, smaller liquid. It's the rule. That's what we have. Why is it? Well, suction, or low side, is a vapor, right? It's a gas. What happens with gas? Those molecules have expanded, right? Needs more space. Liquid, more dense. We're going to use a smaller space. So the suction line is always bigger than the liquid line. Or if you want to really get into it, the liquid line is always smaller than the suction line, whichever way works for you. This liquid line, the smaller one, when you're doing an install, let's say you're doing an install for a customer who says, look, no way, Ryan, are you going to put that ugly box next to my beautiful house. I want it as far away that I don't see it. And I definitely don't want to hear it. I don't want to hear this thing run. So you say, well, we can do something maybe 75 feet away. And they say, fine, that's good. As long as I don't see it, as long as I don't hear it, I don't care. Well, if it, systems come with what's called a factory charge of refrigerant. And let's say that factory charge is 7 pounds. That factory charge is generally good for what's called 50 foot of line set. Well, what's line set? Line set is the combination of the suction line and the liquid line. The big one and the littler one. So anytime you go beyond, let's say 50 foot, you have to read the specifications for whatever you're installing. Well, let's say it's 50 foot. Whenever you install more than 50 foot of line set, then you're going to tell you that for every foot extra over 50 of liquid line, you have to add 1 ounce of refrigerant. So if you have 25 extra feet of liquid line, that would mean that that unit that had 7 pounds of refrigerant now requires 7 pounds and 25 ounces. And you can do the conversion for the math for the pounds. When you're charging, you're usually going to set your weigh scale on ounce and convert everything to ounce. It makes it easier. Instead of you trying to convert pounds and ounces in your head. So it just makes life a lot easier. So, suction line, liquid line. Bigger, smaller. The other thing about suction lines have to be insulated. He gets to wear a little coat. We want the suction line to be insulated because the suction line is what's being suctioned. It's going back, it's the return line back to the evaporator. And so this is coming from the evaporator. So if the evaporator by design was liquid refrigerant equaled 40 degrees, it absorbed that heat and absorbed it until it became a superheated vapor, then that target superheated vapor is anywhere from a sensible temperature of 8 to 12 degrees warmer than that 40 degrees. So as it's traveling back, particularly if it's 75 feet, that's a long way. We have to make sure we keep it stabilized, temperature, so it does not change states of matter and goes back to being a liquid, which would destroy our compressor. So that's why you see this black stuff right here. And if you look around in the room, you'll see the lines have been covered, insulated with this. So suction lines are insulated. These days, if you have a ductless system and you order the line set, they'll ask you, do you want 25 foot or you want 50 foot for your install? Usually, well, not usually, they do. They come and they're bundled together with this insulation liquid line and the suction line together. And you also put your wires with it. So if you look, you'll see all the wires are bundled together, as well as the drain line, the condensate line. So the last item that the chapter talks about is suction line filter dryer. Now we have one of these right over here. So another complex concept here. The suction line filter dryer looks different than the liquid line because one's bigger, one's smaller. This one, remember, we check with temperature to see if it's at capacity. This, we check with gauges. So you look at the gauge pressure of it going in, and then you measure the gauge pressure going out. And if you get more than 3 psig, this is at its capacity, no longer any good. That's chapter 6 right there. So what do you think? Any questions about that?